In 1901, Guglielmo Marconi transmitted a signal across the Atlantic Ocean. Critics said it would have been impossible, but the signal arrived. It should have bounced off the Earth curvature, but it had bounced off an invisible, electrified layer around the Earth, the ionosphere. Marconi had proved that this layer exists, and for over a century they've used it to communicate. But for astronomers, that same layer is a nightmare. Imagine for a moment looking at the stars, but it's pouring rain. The image will be shifted, distorted, and blurry. For modern radio telescope, like the European Low Frequency Array, or LOFAR for France, the ionosphere acts exactly like the rain. For them, it is just noise. But in my research, I asked, what if we stopped looking through the rain and we begin to study the storm itself? I transformed the LOFAR from a radio telescope into a powerful new tool to better understand the Earth's own ionosphere. You know, with many traditional instruments like GPS, we can see the broad picture, the global ionosphere, but with LOFAR, I was able to capture irregularities smaller than 10 kilometers. But the real test arrived on Mother's Day in 2024. It was the biggest storm in the last 20 years, and many instruments were blinded by it. But not LOFAR. LOFAR kept watching. And what we discovered was something incredible. You know, many traditional simple models assume that most of the ionospheric irregularities sit at an altitude of around 300 kilometers. But with a method that I developed, I proved that during this storm, the effective altitude of the irregularities jumped up to 1,500 kilometers, an altitude rarely matched by ground-based instruments. We weren't just looking at the storms. We were looking at a system so disturbed that our models fail. Marconi have proved that the ionosphere exists. But for over a century, we have just looked at it. With my research, I proved that we can use astronomical noise, we can transform it into physical signal to better understand it. Thank you.